this equation shows us the relationship between energy and frequency of light using Planck's constant. Let's put this in here. So the energy of a photon, which is a packet of energy. The word photon was actually coined by Einstein, but Planck came up with the idea that energy is quantized, not continuous. It's kind of like stairs. You can be on one stair and second stair and third stair, but you can't be in between. It's one way to think about it. Anyway, Planck studied how objects glow when they're heated and the light that comes off from them, and he found that only certain wavelengths of light would be released. Again, Einstein coined the word photons to describe these packets of energy. And then also the relationship is that the higher the frequency, the greater the energy. He used this idea to explain the photoelectric effect, which we will talk about in a minute. Electromagnetic spectrum, and talk about its energy. So first I'm going to label the energy here. The highest energy is the gamma rays. And the lowest are the radio waves. Okay, and from what we said before, higher energy comes from higher frequency. And a high frequency comes from a short wavelength. So small or short wavelength. Long wavelength. Okay, so there's our spectrum. And so if you look at these types of radiation, the most dangerous types are at the top. These are the types that will harm your tissue by damaging your DNA and proteins and stuff. So gamma rays are very high energy radiation. This is where you talk about a radiation burn or something from uranium or whatever the isotope is. So very damaging. X-rays are also damaging, but not as much so. If you get a lot of X-rays, it can put you at risk for cancer, but it's definitely not as damaging as gamma rays. UV light, you know that is damaging to your skin. Visible light, as far as it touching, hitting your body, is not so damaging at all. It doesn't have enough energy to be. Infrared light, this is the light that a warm body, you, will emit all of the time, infrared radiation. And the night goggles that are used to see a person in the dark is actually viewing this type of radiation. Microwaves have less energy. That may seem strange, but the deal is that microwaves have just the right amount of energy to make water molecules vibrate and warm up. And so it's just the right frequency for warming up the water. And so that's how they heat up food. Okay, and then radar, like weather radar, and radio waves, you know what that is. We need to say more about the visible light because you need to know the spectrum. And maybe you learned Roy G. Biv. I'm going to write that. Okay, notice I wrote it kind of upside down because I wanted to put the highest energy type at the top. So let's fill these in. Indigo is a color kind of between blue and violet. Okay, so there's our rainbow. And again, this is in order, so this is the highest energy, and red is the lowest. If you want to remember which end of the rainbow is the highest, just remember that ultraviolet, UV, would be up here. That's why it's ultraviolet. And then infrared is below red or beyond red. It's down here. So that gives us the order. So like you need to know that a blue light has more energy per photon than an orange light. Here is the spectrum again with the different wavelengths and frequencies labeled. This can come in handy when you are doing the experiment and you determine that a photon has a wavelength of, say, 600. You could see what color 600 nanometers relates to. By the way, these numbers that tell you the ends of the visible range, they actually vary depending on the source that you use, because actually all of our eyes are not exactly the same as far as how much you see down there. I mentioned the photoelectric effect. This was studied by Einstein, and the idea that you have packets of energy explained the photoelectric effect. In order for this to happen, so what the photoelectric effect is that if you shine a light on metal, sometimes an electron is given off. And the electron has a specific energy, can have specific energies. The light that is shown, when we say light, we mean photons. So the idea is that one photon must contain enough energy to knock one electron out of its atom. And so if one packet of energy doesn't have enough, the photoelectric effect won't occur. And so, for example, potassium can emit electrons with when you shine violet light on them, but not red light. And that's because one photon of violet light has more energy, and a photon of red light has less, and it doesn't have enough to knock that electron out.